Hello everyone, this is P. Mabu Hussain, Assistant Professor of EEE from Institute of Aeronautical Engineering, Hyderabad. Today in this video, we are going to discuss about the numerical problems which are related to voltage distribution across a string of insulators, and also solve some of the numerical problems on string efficiency along with this. So this comes under the module 2, mechanical design of overhead transmission lines. So in which we are solving the numerical problems on voltage distribution and string efficiency. Upon completion of this video, the students will be able to solve the numerical problems which are related to the string efficiency as well as the voltage distribution across a string of suspension type insulators. So before going to solve some of the numerical problems, let us recall what is voltage distribution and string efficiency in a suspension type insulators. Okay, suppose if you are taking 3 insulator string, so which means that there are 3 insulators which are connected in series with a metallic link. Now the voltage across the conductor, which is at the lower end of the insulator, and the tower structure, so it is called the total voltage across the string of the insulator. Now how this total voltage is the voltage across the conductor. Now this voltage, which is a phase voltage, is distributed across all the 3 insulators, right? So then what is the voltage across the first insulator, which is V1, what is the voltage across the second insulator, V2, and what is voltage across the third insulator, V3. How the applied voltage V phase will be distributed among all these 3 insulators, right? This we can solve. And then string efficiency. This string efficiency is the ratio of voltage across the whole string. So voltage across the whole string to the product of number of discs and voltage across the disc which is nearer to the conductor. So in simple way, you can express by using this expression. String efficiency is equal to voltage across the total string by total number of discs which are connected in series. So N, and voltage across the disc which is near to the conductor, right? This is the expression for determining the string efficiency. If you want the percentage of string efficiency, this expression will be multiplied with 100. Okay, and voltage across the string is always a per phase voltage. Remember that the 3-phase transmission line system is having the voltage across the string to be a phase voltage. Okay, so in a 3-phase transmission line, you have 3 phases. So, but the insulator is connected between one phase and the tower structure, right? So here, this is the insulator structure, and this is the cross arm of the tower, and which is connected to the ground. So that means this cross arm is connected to the ground. So this can be treated as the earth, and the conductor, live conductor, is connected through this insulator string to the cross arm of the tower. So now the voltage across this insulator string will be the phase voltage, which is nothing but the voltage across one line and ground. Okay, so this voltage V is always a phase voltage. So even if they were given a 3-phase transmission line system with some voltage which is line to line, so then you have to convert that into phase voltage, V phase by √3, right? So V phase value is √3 times the V line to line voltage. Okay, so here in our example, we have considered the total number of discs to be equal to 3. So N value here will be the 3, and voltage across the disc near to the conductor, right? If you see here this picture, voltage across the disc which is nearer to the conductor is V3. So that V3 we are writing here. So multiplied by 100, you will get the percentage of string efficiency. So now let us see the first problem. The problem is that in a 33 kV overhead line, there are 3 units. There are 3 units in a string of insulators. If the capacitance between each insulator pin and earth is 11% of the self capacitance of the each insulator, so then find the voltage distribution over 3 insulators and the string efficiency. Right. So here in this problem, an overhead transmission line is given, and the voltage of overhead transmission line is 33 kV. So now this overhead line is 33 kV in the sense it is a 3-phase transmission line system. So in 3-phase only you will be having high amount of voltage. Okay, it is a 3-phase transmission line, and the voltage represented here is the line to line voltage, which is 33 kV. So as I told before, for calculating the string efficiency, you have to consider the phase voltage. So you have to convert this into phase voltage simply by multiplying with root 3. So VLL is equal to root 3 times V phase. So V phase will be VLL by root 3. So this is the problem. This is the equation actually, right? I think in previous section, this problem we have written reverse. So but the actual equation is if VLL is equal to root 3 times V phase. So from this V phase will be VLL by root 3 how to consider. So here this 33 kV represents the line to line voltage. Okay. So line to line voltage. So to get the phase voltage, you have to divide that with root 3. So that you are getting a per phase voltage which will be equal to 19.05 kilovolts. That means voltage across the total string is a phase voltage. So that phase voltage is 19.05 kilovolts. Now here if you see the problem, they are saying that the capacitance between each insulator pin. So insulator pin in the sense this one, each insulator pin, and earth. So earth here in the sense the tower structure, this one. So the capacitance between this insulator pin and the tower structure or earth is 11% of the self capacitance. Self capacitance in the sense the insulator capacitance, which is C here, right? So for self capacitance of each insulator disk, we are assuming it to be equal to C. Now they are saying that C1, or this is the C1, which is the pin to earth capacitance. So that C1 will be equal to 11% of the self capacitance they are saying. So that means C1 is equal to 11 by 100 into C. So which will be equal to 0.11 C. So this is the value of C1. Now we have defined one term which is called the value of K. So that K is equal to C1 by C. So now from this expression, C1 by C is equal to 0.11. Okay. So like this you can find the value of C. Consider the 3 insulator string and find out the voltage distribution across each insulator string. Okay. So now here at junction A, we are writing the Kcl equation. So Kirchhoff's current law we are going to apply at junction A. So now then I2 will be equal to small I1 plus capital I1. So these capital I1, capital I2, capital I3 are the current flowing in the each insulator disk, and small I1, small I2, small I3 are the currents in shunt capacitances, right? So if you apply the KCL at node number 1 or node A, so here I2 will be equal to I1 plus small I1. Okay. So then here what is the I2? I2 is the current flowing through the self capacitance C. Okay. And voltage across the capacitance is V2. So then the current I2 is equal to voltage V2 by XC, reactance of that capacitance. So this will be equal to V2 by 1 by omega C, which is equal to V2 omega C we can write. So the I2 is equal to V2 omega C. Similarly, I1. So I1 is the current flowing in the insulator disk 1, which is having the same capacitance C, and voltage across the disk is V1. So from this, if you apply the same here, I1 will be equal to V1 by XC. So finally, we will get V1 into omega C. Okay, I1 is V1 into omega C, I2 is V2 into omega C. So then what about the small I1 here? So small I1 is the current flowing through the shunt capacitance, right? So that shunt capacitance value is the some fraction K times the value of self capacitance C, right? This K is simply 0.11. It is already given. So but for problem analysis, we are assuming that the value of shunt capacitance will be K times the value of C. Okay, so that K value here is 0.11. Okay, now the current flowing through this KC is small I1. Okay, if you observe this, current flowing through the KC is the capacitance value of this shunt capacitance, and I1 is the current flowing through the capacitance. So and voltage across this, if you want to observe, right, voltage across this capacitance is nothing but voltage across this pin and this point. So this point is same as this point. So voltage across these 2 points is same as voltage across the Kc. So now, so voltage across this here is the V1. So here also the voltage is V1 only. So in such a case, I1 will be equal to V1 into omega Kc you will get, right? Or simply you can write V1 into K omega C. Okay. So small I1 is V1 into K omega C and capital I1 is V1 into omega C and I2 is V2 into omega C. Now by using all three equations, we can write this equation. So in place of I2, V2 omega C, in place of I1, V1 omega C, in place of small I1, V1 into K into omega C, right? So now from this, here if you observe omega, it will get cancelled. Also the value of C also will get cancelled. So the remaining is V2. V2 is equal to V1 plus V1 into K. So if you take V1 as common, then V2 will be equal to V1 into 1 plus K. So on the value of K is 0.11. So V2 will be equal to V1 into 1 plus 0.11. So finally you are getting the value of V2 in terms of V1 as V2 is equal to 1.11 V1. So let it be equation number 1. So like this, you have to write the KCL equation at node B as well as, so even only at node B is enough, right? So at junction B or node B, if you write the KCL again you are applying the Kirchhoff's current law. So at node B or junction B, here I3 is equal to I2 plus capital I2, small I2 plus capital I2 or capital I2 plus small I2. This is the Kirchhoff's current law equation at junction B. Now here also you can find the value of all the currents in terms of voltages, right? So this I3 is the voltage across this capacitance, current flowing through this capacitance, and voltage across this capacitance is V3. So I3 can be written as V3 into omega into C. And small I3, the small I3 is the, so this small I2 here. Small I2 is the current flowing through this capacitance. Now voltage across this capacitance is nothing but voltage across this point, and this point. But this point is same as this point. So voltage across these 2 points is V1 plus V2. So the value of small I2 will be equal to voltage across the Kc is V1 plus V2. So V1 plus V2 omega into Kc you will get, right? So now the value of capital I2 will be, capital I2 is the current flowing through this capacitance. Here capital I2 is equal to V2 into omega C you will get. So all these equations again you have to substitute here in this equation. So I3 is V3 into omega C, capital I2 is V2 into omega C, and small I2 is V1 plus V2 into K omega C you will get. Okay. So now you again have to cancel out omega C. So then V3 is equal to V2 plus V1 plus V2 into K. So now here the value of V2 in terms of V1 we already know. So value of V2 in terms of V1 from the previous slide is this one. V2 is equal to 1.11 V1. So now in place of V2 you can substitute 1.11 V1. That we are going to do here in this slide. Okay. In place of V2 we are going to substitute 1.11 V1. So here also in place of V2 we are substituting the value of 1.11 V1, and the value of K here is 0.11. It is already given. So now if you solve this, you will get finally the value of V3 in terms of V1, which is equal to 1.342 V1. Okay. So from the previous slide, V2 in terms of V1 is 1.11 V1. So now from this equation, V3 is 1.342 V1. Okay. Now the total voltage across this thing is V or V phase. So this V is nothing but sum of all these three voltages. So V is sum of V1, V2 and V3, and the value of V1 where as it is you are keeping, and in V2 is nothing but 1.11 V1 we are writing here. V3 it is the 1.342 V1 we are writing again. Now Finally, you will get the value of V also in terms of V1, which is equal to 3.452 V1, which is equal to 3.452 V1. So we are getting V is equal to 3.452 V1. Okay, and we already know that the value of V. So the value of V is VLL by root 3. So VLL here is 33 kV. So 33 kV by root 3. So you got 19.05 kilovolts. So this is the V phase, right? So this value you got here. Okay, this is the 19.05 kilovolts So which is about 10 kV we can write 3.452 V1. So from this expression you will get the value of V1. Okay, so the value of V1 will be equal to 19.05 by 3.452. If you solve this, you are getting the value of V1 will be equal to 5.52 kilovolts. Okay, similarly if you use this equation, V2 which is equal to 1.11 V1, and the value of V1 here is 5.52. So if you substitute, then 1.11 into 5.52, the value of V2 will be equal to 6.13 kilovolts. Similarly, V3 is nothing but V3 is equal to 1.342 V1. So again, V1 value here is this value 5.52. If you substitute that, you will get the value of V3 will be 7.4 kilovolts. Right? So this is the voltage distribution across each insulator. You got all the voltages V1, V2, V3. Right? So V1 is the insulator disk which is nearer to the cross arm of the tower. So then V2 is the next insulator, and V3 is the next insulator which is nearer to the conductor. This is the live conductor. Now the voltage, the disk which is nearer to the conductor is this disk. Okay, so while calculating the string efficiency, you have to consider this voltage V3. Okay, so string efficiency, as I said before, this will be equal to voltage across the string by number of insulators or insulator disks multiplied by voltage across the disk which is nearer to the conductor, which is equal to V3. Okay, voltage across the total string is 19.05, which is the value of V. So V by number of insulators here is 3 and the value of V3. Right, V is 19.05 by 3 and V3 value you got here is 7.4. If you substitute all the values, then you are getting the string efficiency will be equal to 85.8%. This is how we can determine the string efficiency for a string of insulator as well as voltage distribution across the string. Now let us see another problem here. So in a three-phase transmission line, right, the problem is a three-phase transmission line is being supported by 3 disc insulator. Again here also the total number of disc in a insulator string is 3 only. The potential across top unit which is nearer to the tower and the middle unit are given here. So K 8 volts and 11 volts. Now here you are having the 3 insulators. Okay, so 3 insulator discs are there. Okay, and here this is the tower structure or cross arm you can say. Right, so now here you have the conductor. So these 3 insulator discs are considered here, and they are giving that the potential across the top unit or voltage across the top unit and middle units are 8 kilovolts and 11 kilovolts respectively. So that means top unit in the sense the unit which is nearer to the tower. So this unit, okay, voltage across this unit is V1, next unit is V2, next unit is V3 if you consider. So then this V1 value and V2 value both are given. V1 is 8 kilovolts, V2 is 11 kilovolts. So they were given. So then you have to calculate the ratio of capacitance between pin and earth to self capacitance of each unit. The voltage, the ratio of capacitance between pin and earth is nothing but this capacitance, shunt capacitance. Okay, and self capacitance is nothing but capacitance of insulator disc itself. Right, so the value of C1 by C, so which is the value of K. So this K value you have to find out. So then line voltage you have to determine. Okay, so line voltage they are saying. So it is a 3-phase system. You have to determine the line to line voltage. What is the line to line voltage? Then finally string efficiency also we have to determine. Okay, right. So again, you are drawing the same 3 number of insulated disc by considering each disc is having a capacitance C here, right? So this capacitance C is the capacitance of each insulated disc, or it also can be called as self capacitance of insulated disc. Then this is shunt capacitance is the k times the value of self capacitance C. Okay, so now you have to find out the value of k here. Okay, so in the problem they given voltage across the first 2 unit, which is near to the tower. This value will be equal to 8 kilovolts, and this value will be equal middle unit V2, which is 11 kV. Okay, right. So whatever procedure we have done in the previous problem, the same we are doing here also. At junction A, again we are writing the Kirchhoff's current law. Okay, so when you write the Kirchhoff's current law, capital I2 will be equal to capital I1 plus small I1. Again, the value of I2 in terms of voltage, you can write voltage across this disk is V2. So I2 can be written as V2 into omega C. I2 can be written as V2 into omega C, which is equal to I1 is nothing but voltage across current flowing through this disk. In terms of voltage, if you written, so then I1 will be V1 into omega C plus small I1 will be V1 into omega into Kc. Okay, so again here omega C will get cancelled. So the value of V2 will be equal to V1 times the 1 plus K you will get. Okay, now you know the value of V2 and you know the value of V1. So the value of K here, you can write it as V2 minus V1 by V1 you will get. Okay, so from this equation, you can write V2 by V1 is equal to 1 plus K. Then the value of K is equal to V2 by V1 minus 1, which is equal to V2 minus V1 by V1. So this formula we are using here. So K is equal to V2 minus V1 by V1. And the value of V2 is the 11 kV. It is given in the problem. V1 is 8 kV. So which is given in the problem. If you substitute, you will get the value of K here directly. So K is 0.375. Okay. So then again you apply the Kirchhoff's current law to node B also, or junction B also. Okay, then capital I3 will be equal to small I2 multiply plus capital I2. Right? This equation you will get here. So now I3 is the current flowing in the third capacitance or third insulated disc. So voltage across the third insulated disc is V3. So if you write I3 in terms of V3, so I3 will be equal to V3 omega C, and I2 in terms of V2 will be V2 into omega C, and small I2 in terms of voltage will be V1 plus V2 into K into omega C. So here also omega C will get cancelled. So then V3 is equal to V2 plus V1 plus V2 into K. Okay. So now here also we know the all values. V2 value already given in the problem, which is 11 kV. V1 value already given in the problem, which is 8 kV. And we already determined the value of K. So the value of K is 0.375. So that value also known here. So if you substitute all the values, you will get the value of V3. Right? So if you substitute all the values here, then voltage across the third unit, which is V3, will be equal to 18.12 kilovolts. Now the total voltage across the string is nothing but sum of all these three voltages, V1 plus V2 plus V3. So V1, V2 are given 8 plus 11, and V3 we calculated, which is 18.12. So the total voltage across the string is 37.12 kilovolts. So this is the phase voltage as already told. So voltage across the total string is nothing but voltage across the one line and earth. So which is the V phase. So if you want the line voltage, you have to multiply the phase voltage with the root 3. So root 3 into 37.12 is the line voltage. So which is equal to 64.28 kilovolts. So now the string efficiency. String efficiency is equal to voltage across the total string, which is V, and total number of insulator, 3 insulator, and voltage across the disk, which is nearer to the conductor, is V3. So multiplied by 100. Right? Total voltage V is 64. So per phase voltage you have to consider. So 37.12, that value 3, V3 value is 18.12. So if you calculate, you are getting the string efficiency which is equal to 68.28%. Right? So here in this problem, instead of asking the voltage distribution, they given the voltage across two units and they asked to find out the voltage across the third unit and total voltage across the string. And also they asked the percentage of string efficiency also. So this is how we can determine for that type of problems. Right, let us see another problem again. So in this problem, so each line of a three-phase system is suspended by a string of three similar insulators. Similar insulators in the sense they will be having same self-capacitance. So which is equal to C we are assuming. So then if the voltage across the line unit is 17.5 kilovolts, line unit in the sense which is nearer to the line. So V3, so here the value of V3 is given which is equal to 17.5 kilovolts. Okay, so then calculate the line to neutral voltage. Line to neutral voltage in the sense phase voltage. So which is equal to voltage across the total string V you have to find out. Okay. So assume that the shunt capacitance between each insulator on the earth is 1/8 times the capacitance of the insulator itself. So then which means that it is the value of K. The value of K is C1 by C. C1 is the shunt capacitance, and this shunt capacitance they are saying that it is the 1/8 times the C. So CC will get cancelled. So the value of K is 1/8. Right? They are giving the value of K indirectly here. Okay. So you have to find the string efficiency also finally. Right? So they are given the value of K indirectly. So which is the ratio of shunt capacitance to self capacitance C. Right? And this shunt capacitance they are given that it will be equal to 1/8 times the self capacitance. So if you cancel this, you will get the value of K which is 0.125. Okay, and they also given the line voltage, line unit voltage. Line unit here is nothing but voltage across the disk which is nearer to the line. So which is V3. Right? The V3 value is 17.5 kilovolts they are given. Okay, now you have to find out the total voltage across the string which is the line to neutral voltage. Okay, so if you want the total voltage which is equal to sum of all the voltage V1 plus V2 plus V3. In our problem only V3 is given. You need to find out V1 and V2. Right, and the value of K also given here. Okay, so again the procedure is same. You have to apply the KCL at junction A. Right, so when you apply the KCL at junction A, capital I2 will be equal to capital I1 plus small I1. So same equation. Again I2 is equal to V2 omega C. I1 is equal to V1 omega C. Small I1 is equal to V1 into K into omega C. Omega C, omega C, omega C will get cancelled. Then V2 is equal to V1 into 1 plus K you will get. Okay, so which is equal to V1 into 1 plus the value of K is 0.125. So you will get finally the value of V2 in terms of V1. So V2 is equal to 1.125 V1. This you are getting finally. Right? So next you apply the KCL at junction B. So if you apply the KCL at junction B, then capital I3 will be equal to capital I2 plus small I2 you will get. Again I3 is V3 omega C, capital I2 is V2 omega C, and small I2 is V1 plus V2 into K into omega C again. Okay, again omega C will get cancelled. So V3 is equal to V2 plus V1 plus V2 into K, and the value of K here is already known 0.125 that we are going to substitute, and from the previous equation the value of V2 is 1.125 V1. So in place of V2 we are going to substitute 1.125 V1. Here also in place of V2 1.125 V1 we are writing. So if you solve this equation, then you will get the value of V3 in terms of V1, which is V3 is equal to 1.39 V1 we are getting. Okay, so from the previous equation V2 is 1.125 V1. Here you can write V2 is equal to 1.125 V1 and V3 here is 1.39 V1. Okay, so but we don't know the value of V1. So but you know the value of V3. So V3 is given in the problem itself, right? What is the value? 17.5 kilovolts. Now in this equation, if you substitute the value of V3, then you will get the value of V1, so which is equal to V3 by 1.39. So the V3 here is 17.5 by 1.39. So then V1 we are getting, V1 is equal to 12.59 kilovolts. So by using this equation, which is you can find out the value of V2. So V2 is equal to 1.125 V1, and the value of V1 we calculated 12.59. So if you substitute that, you will get the value of V2, which is equal to 14.16 kilovolts. Now you got all the voltages. V1 you got, so which is 12.59 kilovolts, and V2 is 14.16 kilovolt. V3 is given in the problem itself, 17.5 kilovolts. So now the total voltage across the string will be sum of all three voltages, right? So voltage between the line and earth, so which is also called as line to neutral voltage, is equal to V1 plus V2 plus V3. So V1 is 12.59, V3 is 14.16, and V3 given in the problem 17.15. So if you sum all this, you will get the line to neutral voltage, which is equal to 44.25 kilovolts. Okay, so this is the total voltage across the string V. Okay, so now the string efficiency you can easily find out. String efficiency will be equal to voltage across the total string V by total number of insulators, here is 3, multiplied by voltage across the disk which is nearer to the conductor. So this is the conductor. So voltage across the disk which is nearer to the conductor is V3 here. So multiplied by 100, you will get the percentage of string efficiency. So V 44.25 by 3 into V3 is 17.5, which are already given in the problem. So finally you are getting string efficiency will be equal to 84.28%. Okay, this is how we can determine the string efficiency if one voltage is given across any unit. Okay. Then let us see another problem. Okay. So here in this problem, the self capacitance of each unit in the string of 3 suspension insulators is C. So they are given that self capacitance of each insulator disk will be C, and the shunting capacitance of the connecting metalwork of each insulator to earth will be 0.15. So here what they are saying is you have 3 insulators. Okay, so 3 insulators they are saying. Now this each insulator is having some capacitance. Okay, and the capacitance will be C. Okay, so now the shunt capacitance, which is the capacitance between this metallic connecting metal and tower structure, so which is the earth here. So this capacitance they are given, which will be equal to 0.15 C, and they are also giving that for line the same shunt capacitance is 0.1 C. So that means between this insulator pin and here you are having the line, right? So now between this and line also there is another capacitance, and that capacitance value they are giving that this is 0.1 C, right? Similarly here also you have the one insulator pin, between earth you are having 0.15 C, and between line and that pin you will be having 0.1 C. So this is the structure. So we have to draw the diagram before we are proceeding with the problem. Okay. So the same thing here it is represented here. Okay. So 0.15 C is the shunt capacitance between metalwork of each insulator to earth. Earth here is nothing but tower. Okay. So this is given as 0.15 C. While for line it is given as 0.1 C. Right. From the same point to the line it is 0.1 C. Okay, so now here you have to assume the direction of currents. So let us assume that current flowing through each insulator disk. So from top to bottom, so insulators are numbered with 1, 2, 3. So voltage current flowing through the first insulator is I1, second insulator is I2, third insulator is I3, and voltage is V1, V2, V3 same. Okay, Now current flowing through the sent capacitance, you can treat them as I1 dash and I2 dash, or I1 I1 dash, I2 I2 dash, like that. Okay. So now it's the same procedure you have to repeat again. Each time you have to write the KCL at junction A as well as junction B. Right, at junction A we are writing the KCL equation. Right, now from here if you write the KCL equation, so incoming currents are these two currents, capital I2 and I1 dash. Okay, incoming currents are I2 I1 dash is equal to outgoing currents are small I1 capital I1. So I1 plus capital I1 plus small I1. Incoming currents is equal to outgoing currents, you can write. Now these current we have to express in terms of voltages. Right. So here voltage across each insulator is V1, V2, V3 here. Okay. Now I2 is the voltage across, sorry, I2 is the current flowing through this second insulator. So now voltage across this is V2. So I2 you can write it as V2 into omega into that capacitance value C. Okay. I2 is V2 into omega C. So then what is I1 dash, small I1 dash, this value. This is the current flowing through this capacitance, which is the value is 0.1 C. And voltage across this point and this point. This point is same as the line. So this point, right? So voltage across these 2 points you have to see. So voltage across these 2 points is sum of V2 plus V3. So I1 dash will be equal to V2 plus V3 multiplied by omega into value of capacitance is 0.1 C. This you have to write. In place of I1 dash, we are writing V2 plus V3 0.1 omega C. Okay. So then in place of I1 we can write I1 is the current flowing through this disk and voltage across this is V1. So I1 is equal to V1 into omega C we can write. So then small I1 here is this one. Current flowing through the sent capacitance here. This capacitance. Okay. Voltage across this capacitance is capacitance between this point and tower. So or this point, this tower is same as this point. Okay. Voltage across this and this both are same, which is equal to V1. So V1 into omega into that capacitance value is 0.15 C. Okay. So small I1 is equal to V1 into omega into 0.15 C you will get. So from this 0.15 into C into V1 omega you can write. Right. So then if you observe this equation in both sides, omega C will get cancelled. Okay. So now if you reduce the equation, so then you will get this equation. So 0.1 times V3 is equal to 1.15 V1 minus 1.11 V2. Okay. And if you get, if you write only for V3 is equal to 11.5 V1 minus 11 V2 you are getting. So this is the final equation we are getting here. Similarly, we have to write the Kcl equation at junction B also. At junction B, if you observe, incoming currents here, capital I3 and small I2 dash. Outgoing currents are small I2 and capital I2. So incoming currents is, sum of incoming currents is equal to sum of outgoing currents is the Kcl. Okay. Again, these you can express them in terms of voltages. So then I3 is again same, which will be equal to V3 into omega C plus I2 dash. I2 dash is nothing but current flowing through this. So voltage across this key is nothing but voltage across this and voltage across these two is same. So which is V3. So V3 into omega into and capacitance value is 0.1 C, which is equal to capital I2. Capital I2 is the current flowing through this this capacitance, which is V2 into omega C. And small I2 how we can determine? How small I2 is the current flowing through this capacitance, which is 0.15 C. Okay. So now voltage across this you have to observe. So which is nothing but voltage across this point and this point. So this point again it is same as this point. So voltage across these 2 points is V1 plus V2. Right. So V1 plus V2 is the voltage omega and capacitance is 0.1 C. Okay. So again we are reducing this equation by cancelling out the omega c on both sides. Then finally you are getting 1.11 V3 is equal to 1.15 V2 plus 0.15 V1 you are getting. Okay, so now here in this equation we are going to substitute the value of V3. Okay, so V3 is here. So in place of this V3 we are writing this equation 11.5 into V1 minus 11 V2. Okay, so then this equation can be written as this equation. So then from this equation you are getting 13.25 V2 is equal to 12.5 V1. Then V2 you are getting 12.5 by 13.25 into V1. So then again this V2. So this V2 we are going to substitute in the first equation. Okay. So first equation is this equation. Okay. So then in terms of in place of V2 we are going to substitute that value here. Okay. So then V3 is equal to 11.5 V1. 11.5 V1 from this equation. V3 is equal to 11.5 V1 minus 11 into, in place of V2 we are writing 12.5 by 13.25 into V1. So then you will get this equation. So then if you solve this you will get 14.8 by 13.25 into V1. Okay. So V3 in terms of V1 you are getting here. From this equation V2 in terms of V1 you are getting. So then the total voltage, so which is the voltage across the conductor and earth, is sum of all the voltages V1 plus V2 plus V3. So now V2 is nothing but this is the voltage 12.5 by 13.25 V1 and V3 is nothing but 14.8 by 13.25 V1. So if you substitute those values, then the value of V in terms of V1 you are getting. Okay. So the value of V in terms of V1 is 40.55 V1 by 13.25. Okay. So now what we need to find out here in the problem, you need to calculate the voltage across each insulator as a percentage of line voltage to earth. So that means line voltage to earth is nothing but total voltage V. So you have to find out the voltage across each insulator, which is V1, V2, V3. So each voltage as a percentage of V. So that means you have to divide with V and also multiply with 100. So these values you have to find out. Okay. So V1 by V multiplied by 100, V2 by V multiplied by 100, V3 by V multiplied by 100. These values we have to determine. Okay. So now, from this equation, what you can write? V1 will be equal to 13.25 V by 40.55. So from this you will get V1 by V is equal to 13.25 by 40.55. So if you multiply with 100 you will get the percentage. So that value is 0.326 V, or if you want the percentage 32.6%. Okay. And V2 is, so V2 by V1 V2, so V2 here, so from this equation, so V2 is 12.5 13.25 V1, right? So here first initially without finding the percentage we are writing V1. So V1 is equal to 13.25 by 40.55 V, so which is finally 0.326 V. So then V2, if you use that equation, 12.5 into 0.32 V by 13.25. So you will get 0.307 V. So then V3, so from this equation 14.8 by 13.25 V1. So in place of V1, if you substitute 0.326 V, so then you are getting V3 is equal to 0.364 V. So what we are doing here is, we are writing all voltages across each insulator V1, V2, V3 in terms of voltage V. Okay. So now from all these equations you can write V1 by V multiplied by 100 will be 0.326 multiplied by 100, which is 32.6%. So from the second equation V2 by V multiplied by 100 will be equal to 0.307 multiplied by 100, which is 30.7%. And V3 by V multiplied by 100 will be equal to 0.364 multiplied by 100, which is 36.4%. So these are the percentage, voltage distribution across each unit as a percentage of total voltage. Okay, so 36.2%, so 32.6%, 30.7%, 36.4% we are getting. So now you have to determine the string efficiency also, right? String efficiency is this is nothing but voltage across the total unit, which is V, multiplied by total number of discs, which is 3, multiplied by the voltage which is nearer to the conductor is V3. Okay, so now the value of V, you are taking as this by 3 into V3 value in terms of V, you already know, which is 0.364 V, 0.364 V. So this V will get cancelled. If you multiply with 100, you will get the percentage of string efficiency. So that value is 91.5% we are getting. Okay, so this is how you can determine the voltage distribution across each unit as a percentage of line to earth voltage. Okay, this is a very important problem. So finally, the last problem. So each line of three-phase system is suspended by a string of 3 identical insulators of self-capacitance C. Here each insulator self-capacitance is given, which is C here. So this is C, this is C, this is also C. And the shunt capacitance of connecting metalwork of each insulator is 0.25 to the earth. So that means from metallic link to earth it is 0.25, and to the line it is 0.1 C. Then calculate the string efficiency of the system if the guard ring increases the capacitance to the line of the metalwork of lowest insulator is 0.3 C. Right? So they are giving that if you are using a guard ring, so then that guard ring will increase the lowest insulator disc capacitance to 0.3 C from 0.1 C. Right? Before it is 0.1 C. After the guard ring here, if it is placed, that will become 0.3 C. Okay, so the final diagram is this one. So right, so V1, V2, V3 are the voltage across the each insulator disc. Okay, so now here you have to calculate the string efficiency of the total system. If you want the string efficiency, that string efficiency is equal to total voltage by to number of disc 3 multiplied by V3. So here you need to find out the V and you need to find out the V3 also. Okay. So now it is similar to the previous problem. So just you have to apply the KCL at node A, KCL at node B. When you apply the KCL at junction A or node A, you are getting V3 is equal to 12V1 minus 11V2. Right? So if you apply the KCL at junction B, we are getting this equation 1.3 V3 is equal to 1.2 V2 plus 0.2 V1. Again, similar to the previous problem, in place of V3, you have to substitute this equation. Okay, so then you will get V2 in terms of V1, which is equal to 0.993 V1. Now this V2, which is equal to 0.993 V1, you need to substitute here in the second equation, right? So then you will get the value of V3 in terms of V1, which is equal to 0.77 V1, right? So then the total voltage will be equal to sum of all the voltages V1 plus V2 plus V3. So then V2 here in terms of V1 is 0.993 V1. V3 in terms of V1 is 1.077 V1. So if you substitute those values, then you will get the voltage V in terms of V1. Okay. So the voltage V is equal to 3.07 V1 we are getting. So now the string efficiency is equal to, as I said, V by 3 into V3. So now this total voltage V is 3.07 V1 by 3 into what is V3? So V3 in terms of V1 is 1.077 V1. If you want percentage, multiply with 100. So V1 you will get answer. Then if you solve this, you will get the string efficiency, which is 95%. So this is how we can determine the string efficiency for different problems, and you can even find out the voltage distribution. Right? If you want the string efficiency, then obviously we have to determine the voltage distribution across each unit. Okay, so this is how we can determine the string efficiency for different cases. Right, once you go through this sixth problem, this is also similar to those problems, but here number of disks are increased. So here also you have to apply the same procedure. You have to apply the KCL at each node. So then you have to find out the required capacitance. Okay, you can verify this. So here I am ending. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.